The cosmic silence. For as long as we have looked to the stars, we have felt a profound sense of both wonder and isolation. In the grand silent theater of the cosmos, we are, to our knowledge, the only audience. But are we truly alone? This question is perhaps the most fundamental one we can ask about our place in the universe. The vastness of space seems to mock the idea of our uniqueness, while the utter silence that greets our radio telescopes seems to confirm it. This is the great paradox of our time. This is not an exploration of sightings or conspiracies. It is a journey into the realm of the possible, a theoretical expedition guided by the laws of physics, chemistry, and biology as we understand them. Its purpose is to construct a scientifically grounded framework for what alien life, from the simplest microbe to the most complex intelligence, might actually be like. By exploring the probabilities, the environments, and the evolutionary pressures that could exist on other worlds, we can begin to paint a picture of life beyond Earth, a picture built not on fiction, but on the logical extension of fact. We will venture from the atomic building blocks of life to the potential psychologies of sentient beings, from the shimmering oceans of distant moons to the strange biologies that might thrive under alien suns. This is the story of the life that could be, waiting to be discovered in the darkness between the stars. The cosmic context, an ocean of worlds. To grasp the likelihood of extraterrestrial life, we must first appreciate the scale of the universe. Our Sun is one of approximately 200 billion stars in the Milky Way galaxy. Modern astronomy now tells us that most of these stars have planets. The Kepler Space Telescope and subsequent missions have revealed that rocky Earth-sized planets are not rarities, but common occurrences. And the Milky Way itself is just one of an estimated 2 trillion galaxies in the observable universe. The raw numbers are staggering. If every star in our galaxy had just one planet, that would be 200 billion worlds in our cosmic backyard alone. If only 0.1% of those were capable of supporting life, that would still leave 200 million potentially living worlds. This perspective is rooted in a core scientific principle known as the Copernican principle, or the principle of mediocrity. It posits that there is nothing special about Earth or our place in the universe. Just as Earth is not the center of the solar system, our solar system is not the center of the galaxy, and our galaxy is not the center of the universe. By extension, the conditions that led to life here, a rocky planet, liquid water, a stable star, are likely not unique. Life, the principle suggests, may be a common cosmic phenomenon. In the 1960s, astronomer Frank Drake attempted to formalize this line of reasoning with what is now known as the Drake equation. The equation itself does not provide a definitive answer, but rather a framework for organizing our ignorance. It multiplies a series of probabilities: the rate of star formation, the fraction of those stars with planets, the number of those planets that are habitable, the fraction of those on which life actually arises, the fraction of that life that becomes intelligent, the fraction of intelligent life that develops detectable technology, and finally, the length of time such a civilization remains detectable. While most of these variables are unknown, the equation serves a vital purpose. It shows that even with conservative estimates, the potential number of civilizations in our galaxy alone could range from 0 to millions. It transforms the question from a philosophical musing into a quantifiable scientific problem. The cosmos is not an empty desert. It is a vast ocean of potential, dotted with countless islands we call worlds. The search for life is the exploration of that ocean, the blueprint of life, origins and possibilities. On Earth, life began. How it began remains one of science's greatest unanswered questions, but the prevailing theory of abiogenesis suggests that it arose from non-living matter. In a primordial soup of chemicals, energized by lightning or the heat from deep-sea hydrothermal vents, simple organic molecules spontaneously organized into more complex structures. These structures eventually formed self-replicating molecules, likely based on RNA, which laid the foundation for DNA and the first simple cells. From a single common ancestor, all life on Earth, from the smallest bacterium to the largest whale, evolved. This terrestrial origin story provides a crucial starting point, but it may only be one recipe for life. The first and most likely form of extraterrestrial life we will encounter is microbial. For the first 3 billion years of Earth's history, life was exclusively single-celled. Complex, multicellular organisms are a relatively recent innovation. On other worlds, life may have started but never progressed beyond this microbial stage, existing as vast, unseen biospheres in alien soils or oceans. To find these biospheres, we must broaden our definition of habitable. The discovery of extremophiles on Earth has revolutionized our thinking. These are organisms that thrive in conditions that would be lethal to most other life forms. We have found bacteria living in the boiling water of geothermal springs, in the crushing pressure of the deepest ocean trenches, in highly acidic or radioactive environments, and frozen solid in Antarctic ice. These extremophiles prove that life is far more resilient and adaptable than we ever imagined. They suggest that life could exist on planets we once dismissed as hostile, in the subsurface brines of Mars, the sunless oceans of Europa, or the methane lakes of Titan. This resilience invites us to consider a more radical idea: alternative biochemistries. All known life on Earth is carbon-based and uses water as a solvent. Carbon is exceptionally good at forming complex, stable molecular chains. Water is an excellent solvent, facilitating the chemical reactions necessary for life. But are they the only options? Scientists have theorized that silicon could, under certain conditions, replace carbon as the backbone of life. Silicon sits just below carbon on the periodic table and can also form 4 bonds, allowing for complex molecules. However, silicon bonds are less stable, and its oxide, silicon dioxide, is a solid, sand, or quartz, at most temperatures, which would create significant biological challenges for respiration. A silicon-based life form would likely require a very different environment, perhaps a world much colder than Earth with a non-aqueous solvent, like liquid methane. And what of the solvent? On a cold world like Saturn's moon Titan, with its surface temperature of -180 degrees Celsius, liquid water is an impossibility. But Titan has rivers, lakes, and seas of liquid methane and ethane. Could these hydrocarbons serve as a solvent for a different kind of life? Such a life form would have a profoundly slow metabolism due to the extreme cold, but it is not a theoretical impossibility. Life, it seems, might not be constrained by our Earth-bound example. It might simply follow the laws of chemistry and adapt to the local conditions, whatever they may be. Cradles of existence, where to look for life. The search for extraterrestrial life begins with identifying potential homes. The classic concept is the habitable zone, or Goldilocks zone, the orbital region around a star where the temperature is just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Earth sits comfortably within our sun's habitable zone. However, our understanding of habitability has grown far more nuanced. Within our own solar system, the search has focused on a few key locations. Mars, our red neighbor, is a primary candidate. Evidence overwhelmingly shows that billions of years ago, Mars was a warmer, wetter world with rivers, lakes, and possibly even an ocean. While its surface is now a cold, irradiated desert, water ice persists at its poles and potentially in liquid brine reservoirs underground. If life ever arose on Mars, it could still survive in these sheltered subsurface niches as hardy microbial colonies. Further out, the moons of the gas giants offer tantalizing possibilities. Jupiter's moon Europa is covered by a thick crust of water ice, but beneath it lies a vast, global liquid water ocean, estimated to contain more than twice the amount of water in all of Earth's oceans combined. This ocean is kept liquid not by the sun, but by tidal heating. the constant stretching and compressing of the moon by Jupiter's immense gravity. This process could generate energy and create hydrothermal vents on Europa's seafloor, similar to the vents on Earth that support rich ecosystems teeming with life, independent of sunlight. Saturn's moon Enceladus also possesses a subsurface ocean, and NASA's Cassini spacecraft flew through plumes of water vapor erupting from its surface, discovering organic molecules and silica, evidence of active hydrothermal processes. Beyond our solar system, the possibilities multiply. We are discovering an incredible diversity of exoplanets. There are super-Earths, rocky worlds larger than our own, which could have stronger gravity and thicker atmospheres, potentially making them even more suitable for life. There are planets orbiting red dwarf stars, the most common type of star in the galaxy. Life on such a planet would face challenges, like tidal locking, where one side permanently faces the star, and intense stellar flares. But its biochemistry could adapt. Eyes might evolve to see in the infrared spectrum dominant in a red dwarf's light, and organisms might use bioluminescence to communicate and navigate in the dim conditions. Even gas giants, once thought to be inhospitable, could harbor life on large Earth-like moons orbiting them, much like Europa or Enceladus. The universe has provided an almost infinite variety of stages upon which the drama of life could unfold. Forms and functions. The plausible alien. Speculating on the physical form of alien creatures is a venture into the hypothetical, but it can be guided by the universal constants of physics and the principles of evolutionary biology. The environment of a world will be the primary sculptor of the life that evolves there. Gravity is a fundamental constraint. On a low-gravity world, life could grow tall and slender, as it would require less structural support to fight gravity's pull. We can imagine forests of towering, delicate flora and graceful, long-limbed creatures that move with an effortless bound. Flight would be far easier, perhaps leading to enormous aerial creatures that spend their entire lives in the sky. Conversely, on a high-gravity super-Earth, life would be built for strength and resilience. Creatures would likely be low-slung, stocky, and powerfully muscled, with thick, robust skeletons. Plants might resemble armored plates, hugging the ground to resist being crushed by their own weight. The composition and density of an atmosphere would also shape biology. In a thick, soupy atmosphere, even large organisms might float, suspended like plankton in a cosmic ocean. Sensory organs might rely more on sound or pressure changes than on light. In a thin atmosphere, respiration would need to be incredibly efficient, perhaps involving large, complex, lung-like structures, or even direct chemical absorption through the skin. The light from the parent star dictates the nature of sight and energy. Around a dim red dwarf, photosynthesizing organisms might be black or deep purple to absorb as much light as possible across a broad spectrum. Animals could evolve massive, sensitive eyes to capture every stray photon, or they might abandon sight altogether in favor of echolocation or electrical senses. Bioluminescence could become a dominant form of communication and predation in a world of perpetual twilight. Beyond animal-like life, we can theorize about other forms. A planet with a static, non-rotating position relative to its sun could have a terminator zone, a permanent band of twilight between a scorching hot day side and a frozen night side. In this zone, perhaps life could exist as vast, networked fungal colonies, drawing heat from one side and minerals from the other. Silicon-based life forms on a frigid methane world might resemble living crystals, with metabolisms that operate over geological timescales, appearing inert to our frenetic biology. What we perceive as a rock might be a creature living its life over 1 million years. The central tenet of speculative xenobiology is that life will use whatever materials and energy sources are available and will adapt its form to the physical pressures of its environment in the most efficient way possible. Nature, on any world, is a brilliant and pragmatic engineer. The web of life, alien ecology and behavior. No organism exists in isolation. Wherever there is life, there are ecosystems, intricate webs of interaction, competition, and codependence. The fundamental driving force of any ecosystem is the flow of energy, and this is unlikely to be different on another world. At the base of the food web would be producers, organisms that create their own food. On Earth, this is primarily done through photosynthesis. On another world, plants might use different pigments to capture different wavelengths of light, resulting in forests of red, blue, or black foliage. In the sunless depths of a subsurface ocean like Europa's, the producers would be chemosynthesizers, microbes that derive energy from chemical reactions around hydrothermal vents. From there, the web diversifies. Herbivores would evolve to consume these producers, developing specialized mouths for grinding tough alien flora or filtering chemosynthetic bacteria from the water. In turn, carnivores would evolve to hunt the herbivores. The principles of predator-prey dynamics are universal. A predator needs tools for the hunt: speed, strength, stealth, or venom. Prey needs tools for survival: armor, camouflage, speed, or toxins of its own. Imagine a six-legged predator on a low-gravity world, capable of explosive leaps to ambush its prey. Or an ambush hunter on a jungle planet, perfectly mimicking the color and texture of the surrounding foliage. Symbiosis, the act of different species living together, is another powerful evolutionary strategy. We might find mobile animal species that host photosynthetic or chemosynthetic algae within their tissues, essentially carrying their own food source with them. Or we might find a complex relationship between a burrowing creature and a planet-wide root system, where one provides shelter and the other provides nutrients. Reproduction, the drive to pass on genetic information, could take on myriad forms. Beyond the binary male-female system common on Earth, a species could have 3 or more sexes required for reproduction, promoting genetic diversity in unique ways. Some creatures might reproduce asexually through budding, or release spores that travel on the wind to colonize new territories. Communication would be tailored to the environment. In a dense atmosphere or murky ocean, sound might be the primary medium, leading to complex languages of clicks, whistles, and deep resonant calls. On a world with a thin atmosphere, visual signals like bioluminescent flashes or subtle color changes could be more effective. Chemical communication through pheromones, a language of scent, could be incredibly sophisticated, conveying complex messages about identity, territory, and mood across vast distances. The alien world would not be silent. It would be filled with the hum, flash, and scent of a biology entirely its own. The spark of a mind, intelligence, and civilization. What does it mean to be intelligent? On Earth, we often associate intelligence with tool use, complex language, and self-awareness, qualities that define our own species. But this may be a narrow view. Intelligence is fundamentally a tool for problem-solving. An octopus, which can solve puzzles, use tools, and learn by observation, is highly intelligent, yet its mind is radically different from ours, distributed through its 8 arms as much as its central brain. On an alien world, intelligence could evolve in forms we might not even recognize. It does not have to be humanoid. Imagine a collective intelligence, a hive mind like an insect colony, but with a unified consciousness, where the individual has no self-concept, but the whole is sentient. Or consider a planetary intelligence, like the hypothetical sentient ocean of Stanisław Lem's Solaris, where the planet itself is the organism, its thoughts manifesting as complex physical structures on its surface. Intelligence could also arise in a species without manipulative appendages like hands. A race of aquatic, whale-like beings might develop a profound philosophical and musical culture, but they would never build a radio telescope. Their intelligence would be entirely internal, a universe of thought without the ability to physically alter its environment. The development of technology, the kind we are searching for with SETI, the search for extraterrestrial intelligence, likely requires a specific set of circumstances, manipulative appendages, a social structure that encourages cooperation and knowledge transfer and access to concentrated energy sources. An intelligent species that remains in the hunter-gatherer phase, perfectly adapted to its environment, might see no need to develop advanced technology. Should a civilization arise, it would be shaped by its own unique evolutionary history and planetary environment. A species that evolved from solitary predators might develop a highly individualistic, competitive society. A species that evolved from cooperative herd animals might build a deeply collectivist culture. Their values, their art, their science would all be a reflection of their biology and their world. This leads to one of the most sobering concepts in the search for intelligent life: the Great Filter. This theory suggests that there may be a barrier, or a series of barriers, that are extremely difficult for life to overcome. Perhaps the transition from non-life to life is incredibly rare. Perhaps the leap from single-celled to complex multicellular organisms is the filter. Or perhaps the most difficult step is the one that lies ahead of us: the challenge of a technological species surviving its own success without succumbing to self-destruction through war, environmental collapse, or misuse of its own power. The silence we perceive in the cosmos might be the sound of this filter at work. Echoes in the void, the search for evidence. The search for extraterrestrial life is transitioning from speculation to an observational science. We are developing tools to find not the creatures themselves, but their distant, telltale signatures. These signatures fall into two main categories: biosignatures and technosignatures. A biosignature is any substance, object, or pattern whose origin specifically requires a biological agent. The most promising method for detecting them involves atmospheric spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight shines through its atmosphere. By analyzing the spectrum of this light, astronomers can determine the chemical composition of that atmosphere. The James Webb Space Telescope is designed to do exactly this. A key biosignature would be the simultaneous presence of gases that are chemically out of equilibrium, like oxygen and methane. On their own, they react with and destroy each other. A continuous planetary-scale process, life, is required to keep producing both. Finding such a signature would be powerful, though not definitive, evidence for a living world. A technosignature is evidence of technology. This is the domain of SETI. For decades, we have scanned the skies with radio telescopes, listening for artificial signals against the cosmic background noise. But a technosignature could be more than a radio message. It could be an industrial pollutant in an atmosphere, like chlorofluorocarbons, which do not occur naturally. It could be the heat signature of a massive orbital structure, such as a Dyson swarm, a hypothetical megastructure that an advanced civilization might build to harvest energy from its star. It could be pulsed laser signals used for interstellar communication or propulsion. The search for technosignatures requires us to guess what the byproducts or intentional signals of a different technological trajectory might look like. Direct exploration remains a powerful tool within our solar system. The Viking landers on Mars in the 1970s conducted the first and only experiments designed to detect life on another planet, yielding ambiguous results that are still debated today. Future missions like the Europa Clipper will fly through the water plumes of Europa, directly sampling the contents of its hidden ocean. A Mars sample return mission aims to bring back Martian rock and soil to be analyzed in sophisticated Earth-based laboratories. Historical reports and modern sightings of unidentified aerial phenomena, UAPs, exist outside this rigorous scientific framework. While they capture the public imagination, they lack the verifiable, repeatable, and conclusive evidence required by the scientific method. The vast majority of such sightings are eventually identified as known objects or natural phenomena. For the small fraction that remains unexplained, an extraterrestrial origin is one of a multitude of possibilities, but it is not the default conclusion in the absence of extraordinary proof. Science advances through falsifiable hypotheses and concrete data, and the evidence in this domain has not yet met that standard. The search continues in the laboratory and at the telescope. Weighing the hypotheses, a reality check. In this theoretical exploration, it is crucial to distinguish between degrees of plausibility. The various hypotheses about alien life do not carry equal weight. The most probable hypothesis is that microbial or micro-like life is relatively common in the universe. The building blocks of life, organic molecules, are found in asteroids, comets, and interstellar gas clouds. The principles of self-organization seem to be inherent in complex chemistry. Given the sheer number of potentially habitable worlds with liquid water and energy sources, the emergence of simple single-celled life seems like a reasonable statistical bet. It may be prolific, but hidden, a silent majority in subsurface oceans and deep underground. The existence of complex multicellular life, alien animals and plants, is a step up in uncertainty. On Earth, this transition took billions of years and may have required a series of very specific environmental triggers, such as an increase in atmospheric oxygen. It is entirely possible that most life-bearing worlds remain stuck at the microbial level. However, given enough time and stable conditions, the evolutionary pressures of competition and niche adaptation make the development of complexity a plausible, if not guaranteed, outcome. The least certain hypothesis is the existence of widespread, technologically advanced intelligent life. This is the core of the Fermi paradox. If they exist, where is everybody? The arguments for their rarity are compelling. The evolutionary path to high intelligence may be exceptionally narrow. The great filter might be real and ruthlessly effective. It's also possible our methods of detection are flawed. We might be listening on the wrong radio frequencies, looking for the wrong signatures, or unable to comprehend the communications of a truly alien intelligence. Perhaps advanced civilizations actively choose to be quiet, to avoid detection by potentially hostile neighbors. Or maybe they are simply so far apart in space and time that the odds of any two coexisting and being able to detect each other are infinitesimally small. The most logical conclusion is a tiered one. Simple life is likely, complex life is possible, and technological intelligence is a profound unknown. Our search, therefore, must also be tiered, focusing first on the biosignatures that signal any life at all, while keeping our ears open for the faint, elusive whisper of a technosignature. The human encounter, societal and philosophical ripples. The discovery of extraterrestrial life, even in its simplest microbial form, would be the single most significant discovery in human history. It would trigger a deep and irreversible shift in our understanding of ourselves and our place in the universe. It would be the final act in the Copernican revolution, confirming once and for all that we are not the central point or purpose of the cosmos. The societal impact would be immense. Religious and philosophical systems would be forced to reconcile their doctrines with the existence of another Genesis. Some might see it as a confirmation of a universal creator, while others might face a crisis of faith. Science would be energized, with astrobiology becoming the most vital field of human inquiry. Politics would be reframed. The confirmation of others in the universe might foster a new sense of global unity among humanity, or it could ignite new fears and rivalries as nations vied to control communication or technology. The ethical considerations would be paramount. If we discovered a world teeming with life, do we have the right to visit it, to contaminate it with our own microbes? This is the principle of planetary protection, writ large. If we were to find intelligent life, the questions become even more profound. Do we make contact? The consequences are unknowable. Communication might bring unimaginable knowledge and enlightenment, or it could bring conflict and extinction, either for them or for us. A prime directive of non-interference might be the most prudent yet most difficult path to follow. The nature of the discovery would dictate the reaction. Finding fossilized bacteria on Mars would be a gradual academic revelation. Intercepting a clear, intelligent signal would be a sudden, world-altering event. Humanity would be forced to confront questions we have only ever explored in fiction. What are our responsibilities to other life? How do we represent our entire species? Who gets to decide? The discovery of life beyond Earth would hold up a mirror to ourselves, forcing us to define what it truly means to be human. The path forward. Charting the unknown. The search for life beyond Earth is no longer a fringe science. It is a primary driver of modern astronomy and planetary exploration. Our capabilities are expanding at an exponential rate, and the next few decades promise unprecedented opportunities for discovery. The James Webb Space Telescope and its successors will continue to analyze the atmospheres of hundreds of potentially habitable exoplanets, searching for those tantalizing biosignatures. On the ground, new, massive telescope arrays like the Square Kilometre Array will expand the search for technosignatures by orders of magnitude, scanning the sky with a sensitivity we have never had before. In our own solar system, missions are already in development. The Europa Clipper will map Europa's icy shell and sample its plumes, paving the way for a future lander that could one day melt its way through the ice and send a probe into the hidden ocean below. The Dragonfly mission will send a nuclear-powered quadcopter to Saturn's moon Titan, hopping across its frigid dunes and sampling the organic chemistry of its methane seas. Mars Sample Return seeks to achieve a long-held goal of planetary science, bringing a piece of another world back to our own. The focus is shifting from simply asking, "Are we alone?" to developing a concrete scientific roadmap to find the answer. This involves fostering the interdisciplinary field of astrobiology, which brings together astronomers, biologists, chemists, and geologists. It involves investing in artificial intelligence to help sift through the massive data sets our new instruments will generate. And it involves a global cooperation, a recognition that this is a quest not for one nation, but for all humanity. Conclusion. The grand silence and the grand question. We stand at a unique moment in history. For millennia, we could only look up at the stars and wonder. Today, we are the first generation with the tools to begin a genuine search, to turn speculation into data. We have learned that the universe is not only stranger than we imagine, but stranger than we can imagine. The theories we have explored paint a vast canvas of possibility. Life could be common, but simple and hidden. It could be rare, but when it arises, it diversifies into forms of stunning complexity. Intelligent life could be an ephemeral phase that quickly vanishes, or it could be so advanced that we are simply incapable of recognizing its presence. The silence we have so far encountered may not be an answer. It may simply be the result of our limited instruments, our brief moment of listening in a cosmos that is billions of years old. Or it may be a message in itself, a testament to the precious rarity of the life that blossomed on our small blue world. The search will continue. We will continue to build better telescopes, send smarter probes, and listen with ever more patient ears. We do this not just to find aliens, but to find ourselves. In searching for other life, we are defining our own. Whether we ultimately discover an inhabited galaxy or confirm our profound solitude, the answer will forever change our perspective of home. The grand silence will either be broken or its meaning will become undeniably clear, and either outcome will be a revelation.